This one's going out by request. Number 51, the Atmos Clock, the so-called perpetual motion clock. We've got one here, the Atmos Clock. Gets its name, Atmos, from the fact that it runs off pressure variations in the atmosphere with drive of bellows containing a mixture of gas and liquid ethyl chloride. Because the power to drive these clocks is so limited, they must be very efficient. In fact, a single 60.0 watt light bulb could power 240 million Atmos clocks simultaneously. Find the amount of energy in joules required to run an Atmos clock for 1 day. Let's see if we can do that. Tab. So we're just going to say something like this. Energy equals question mark joules. That's how we measure energy. To run 1 Atmos, typo, watch this. Atmos clock. Atmos, right? Atoms. 1 Atoms clock, not to be confused with an atomic clock. 1 Atmos clock for 1 day. What information have we been given? Well, if you take 60 watt light bulbs look like this. Well, you could run, turns out 240 times 10 to the 6th Atmos. What other information have we been given? Not much. These things are efficient, but I do know that in 1 day, they're asking me about a day. How much energy would it take for 1 day? Well, a day is 24 hours. And as you'll see why in a minute, I converted this into seconds, which is 8.64 times 10 to the 4th seconds. And that's like one of those numbers, if you memorize it, it'll just make life easier. Another one is that 1 hour is 3,600 seconds. Don't forget that. So that's pretty much all we've been given. There's an equation that looks something like this. Power is work over time. So when we're talking about work, we're talking about joules per second. So a watt, this is going to get tricky. This is work, and that's measured, that's an amount of energy. But the unit for this is a watt. Don't confuse the two W's, and a watt is 1 joule per second. So what did I do next? Well, I know that I got to figure out how much work it's going to take. I'm going to be looking for that W right there. But I kind of took a step back for a minute, and I asked a question first. I said, well, this is 240 million clocks, but when you talk about one clock, that's what we're talking about. How much energy for a day? So I did a little conversion, and I said 1 clock. I know that it takes 60 watts to run 240 times 10 to the 6th clocks. So what do you get? It's a small number. I'll write it down here. 2.5 times 10 to the negative 7th watts. It's not a lot of power required to run that clock. 1 clock. We're going to run that clock for a day. So what I did next is I did a little rearrangement. I took my power equals work over time, and I did a little algebra to that, and I figured out that the wattage, the work, see I confused those numbers, the work is equal to power times time, and the power required to run this clock is 2.5 times 10 to the negative 7th watts. And the time that we're going to run this clock is 8.64 times 10 to the 4th seconds. There you go. Now let's take a look at units. I'll do the units up here. A watt is a joule per second, so that's that right there. And then my unit over here is a second. So I'll get a little cancellation action going when I multiply watts times time. And I'll be left with joules. And I got 0.0216 joules. And we do a little moving of the decimal place, and I could say it's 21 thousandths, 21.6 thousandths of a joule, which is 21.6 millijoules, which is the answer in the back of the book. Does that answer make sense? Heck yeah, that's not a little, that's not a lot of energy. That's a very small amount. 21.6 thousandths of 1 joule. Thank you, air pressure. And that was number 51.